It's a real honor to me to have the opportunity to introduce you to Maria Chudnovsky from Princeton University at this WIMSA conference. Maria is maybe one of the most important and representative women mathematicians in the world in the combinatorial and graph theory area. That is my area, that's what I am present in my life. He is recommended for the proof for the strong perfect graph. Let me say a little about that. Just a review. The chromatic number of a graph is defined as the smallest number of colors that can be assigned to the vertices of a graph or a network, with the property that every two adjacent vertices have to receive different colors. And the fifth number is defined as the largest number of pairwise adjacent vertices in a graph or in a network. Trivially, the chromatic number of every graph is at least its fifth number. A graph is perfect if for each of its induced graphs, the chromatic number f of f is equal of the largest number of pairwise adjacent. A whole is a shorter cycle of length and four, and an antihole is the complement of that. 96 Birch announces the conjecture that a graph is perfect if and only if it contains no of and no of and. This conjecture became known as the strong perfect graph conjecture. In May of 2002, Maria Chudnovsky and Pavel Seymour announced that they building on early joint work with Robertson and Thomas has completed the proof of the strong perfect conjecture. The four joint authors presented their work in a workshop in October of 2002 at the American Institute of Mathematics in California, and published a paper of 178 pages in 2002. One of the most surprising things that I want to share at this time is that Maria was, at the time, a doctoral student of Paul Taylor, and as such has been a very inspiring example for many women mathematicians from all over the world in the area of physics. The young woman mathematicians at that time, and not so young, many of us have great admiration for her. For this reason, I am very proud that Nina has continued to present my work. Welcome, Maria, and thank you for being here to share with us this talk. Thank you, Maria.
Okay, can you hear me? Excellent. So thank you very much for such an amazing introduction. I don't know if my lecture will rise to that level, but I'll do my best. It's great to be here. Thank you for coming. So the microphone is okay, everything's okay. So what I'll do today, I'll just give a talk about my field. I'll give a talk about different problems in the area of graph theory that I work in. Most of them are old problems that people started thinking about a long time ago, but they're all problems that gave rise to some part of graph theory, and you can sort of trace what researchers do now back to these questions that were asked hundreds of years ago, decades ago, and can be very easily explained to general audience. So I'm not going to do much of modern science. I'll just hint a little bit at what's being done. I'll mostly talk about history. And again, this is not intended to be representative of anything. This is just problems and theorems I like. So this is not your favorite part of graph theory. I apologize. This is favorite part of mine. My favorite. Okay. So, according to Wikipedia, graph theory was started by Leonard Euler in 1736. Maybe I should tell you. So, I've been working on this stuff for the last 20 years. 20 years ago, somebody asked me for the first time to do Dr. general audience, and I put together a talk. And then every time I hear it, I think of a better way to do it. So I suspect that by now, no connection between 20 years ago and now, except for the one or two slides. But one of the one of the biggest changes happened when I gave this talk at NAT. And at NAT, they're very, very serious. The first talk, we're talking with 2 dates. It's the date for your talk and then the backup date for your talk unless something, in case something happens. And then they look at your slides ahead of time and they give suggestions for what you should do differently. They say you can tell the normal registration and normal something. This is the theoretical mathematician. And so they look at my slides and they said, you should start with the history of the subject. And then suddenly, they like them telling me what to start my talk. And I thought again, they're not, they possibly know what they're talking about. They try and start with the history of the subject. And so I did the first portion of the talk, and I think it makes so much better. So the next few slides are due to math. Oh, so going back to earlier, 1736, the story tells us that in the city of Königsberg, which was then located in Russia and has since moved to many different countries, there was so the geography of the city was as follows. The city is located on 2 river banks. And then so the river is called Pregel, and the city is located on the 2 banks of Pregel. And then in the middle, there are 2 islands. And the different parts of the city are connected together by bridges, known now as the 7 bridges of Königsberg. So there's a bridge between the 2 islands, and then this island is connected to the northern bank, or the top bank, by 2 bridges, and to the bottom bank by 2 bridges, and this island is connected to the top by 1 bridge and to the bottom by one bridge. So just for notation in this picture, green is land, blue is water. Oops. There we do. Green is land, blue is water, and black is bridge. And so the question is, can you design a walk of Königsberg that you start somewhere and finish somewhere, it doesn't matter where, but you walk across every bridge exactly once. So your goal is to look at the bridges. And so Euler thought about this problem, and he said, this is impossible. And why is that impossible? Let's imagine for a second that we didn't actually decide to design a walk. So you start with some landmass, you finish with some other landmass, but every other landmass, you found into it along some bridge, and then you have to leave it along some other bridge. So except for the start and end, every other landmass you visit has to touch an even number of bridges. Enter US. It's not true at the start and end, but it's true at every landmass. So, but now let's look at this picture. The top bank has 3 bridges touching it, the bottom one also 3. The left island has 5 bridges, and the right island has 3 bridges. And what that means is that you have too many landmasses to touch a low number of bridges. Right? You're only the start and end can touch a low number of bridges, and yet here, 4 things touching. So the answer is no, you cannot do that. More than 2 landmasses touch a known number of bridges. So now, as you can probably imagine, this particular story was not made for the great mathematician that he is, because it isn't complicated. But what he did do, he was able to restate this question in a much more abstract way that then we could use to do so much more than an unimportant formula of 7 bridges. So let's see what he said. He noticed that the whole story of water and bridges and landmass is not important. But what's important is that in this problem we have points which correspond to the landmasses, and today's language for the purposes. These are the 4 green points in the picture. So this 4 green points, they correspond to this is that bank, this one is this bank, this one is this island, this one is that island, and then the water is completely unimportant. But what is important is that between different points or land masses, you can walk in different ways. So, for example, from here to there, you have 2 ways in which you can walk, 1 and 2. These are this bridge and that bridge, or between this vertex and that vertex, you can walk in one way along this bridge. And so he created this mathematical model of the problem and using a tool, an abstraction that we now call a graph. So now let me remind you what a graph is. A graph has vertices and edges, and pairs of vertices. If you look at a pair of vertices, they may or may not be connected by an edge or joined by an edge. And so that's a mathematical object I'll be talking about from now on. Euler used it to represent the problem of the 7 bridges of Königsberg. Let's just now see what the question is in terms of the graph. So I'm given a graph with some vertices and some edges. Right now, what I want is to design a walk along this graph, a walk on this graph. What does it mean, a walk? I'm allowed to move between vertices, between a pair of vertices, if these 2 vertices are joined by an edge. And the goal is that I want to walk along every edge, and I want to walk along every edge exactly once. This now we call an Euler walk. Oops, sorry about that. And so then what Euler proved is that in this particular graph, you do not have an Euler walk. Why don't you have an Euler walk? Now let's just say the same thing we said on the previous slide, but in math speak. So in order for there to be an Euler walk, you would need to start and finish somewhere. So there's the initial vertex and the final vertex, but every vertex in the middle, you exit it as many times as you enter it. So that means except for possibly 2 vertices, every other vertex needs to touch an even number of edges. We call it the degree of the vertex. How many edges a vertex touches is the degree of the vertex. So but 2 vertices need to have even degree, and yet here he has degree 5, he has degree 3, he has degree 3, he has degree 3, so there's no Euler walk. All right. Now here's another problem about Euler walks that might be familiar to people in this audience. It's a similar shell. Here, shell. So you're given a drawing, and you want to trace it on a piece of paper, or you do it on a piece of paper without lifting it. Now, what does that mean? It means you start somewhere and keep going. Let's keep going on the drawing, and that's your Euler walk in that drawing. So, for example, here, this is my drawing. So I'm going to record it with vertices, right? The circles as vertices, and then edges joining some pairs of vertices. Now I want to trace it. Well, so now I'm smart. I know that because of the previous slide, I know that I have to start and finish. In order for it to be possible, there need to be exactly 2 vertices of what degree, and that's where I should start, and that's where I should finish. So let's see if it works. So I have this vertex, it touches 3 edges, degree 3. I have this vertex, it touches 3 edges, degree 3. So I know I should start here and finish there. Maybe it's the other way around, but it doesn't matter. And otherwise, actually, theorem tells you can do almost anything you want. And so that's what you do. Start here, you go like this, that, hop, and you finish and you exit. Now, this picture, so it's much more complicated, but you can check that it has exactly 2 vertices of what degree. This one has degree 5, and this one has degree 5, and everybody else has degree 4. And so a theorem tells you that you can trace this, so you can find an Euler walk in this, starting at this vertex and finishing in that vertex. Now I have to tell you it's much harder. Every time I give this talk, I need to, practice for 15 minutes before I can do this tracing. But we're not going to do it together. How many minutes? I said 15, probably. Wow. I've been not my first time. Okay, but you can do it. I promise you can do it. You go out, and then in. More. Okay, so moving on, there's a related problem to the question of Euler walks, and that's that problem of Euler 2. So what's an Euler 2? Well, an Euler walk was we start somewhere, we finish somewhere, and you want to cross every gate that happens. Euler 2 is the same that when you came with the car. So you park your car somewhere, and now you need to come back to the car to pick it up. So it's like an Euler walk that you have to start and finish in the same place. So then what's the difference? Well, now I don't have a start and an end. Okay? Where I started, it's singular. Every time I exit, I have to enter because I need to finish in the same place. So then, in order for another 2 to be possible, it has to be the case that every vertex has a degree. It has to be the case that every lemma actually in a number of bridges. Okay, so that was not hard, right, that we understand. But turns out with the theorem that it's second only. So easy if in order to exist, then everybody is a degree. Hard but not impossible, and in fact true. If everybody has a degree, then there's an order to. So if I give you a graph over the dash and even number of regions, then you can walk around this graph, traversing every area. That's called order. That's pretty clear. Not very hard, it's not very easy yet. Okay, so I won't tell you how to prove this theorem. But this is the beginning of graph theory in 1730s. So now let's fast forward to 1930. That's where my talk used to begin before math. So in 1930, Ramsey, British mathematician Ramsey, asked a spectacular more general question, but this is the question you hear as a student. Is it true or false? Out of every 6 people at a party, there are either 3 that know each other or 3 that don't know each other. And that's what this question is true. And this question is particularly dear to my heart because I suspect that's why I became a mathematician. So the first math question I ever heard, and I just thought it was the most amazing thing in the world. So let's first of all pull this. I had 6 people at the party, so then either 3 know each other, 3 don't. So we'll prove it, and then we'll explain how it's related to graph theory, and then I'll explain how it's related to motion. Here's the proof. Apologies for graphics. So here are my 6 people at the party, and I'm going to look at one of them here, this guy. And so either he knows 3 people or he doesn't know 3, right? He's 1, there are 5 left out of this 5. Either there are 3 that he knows, or there are 3 that he doesn't. So let me assume there's 3 that he knows. Here we are. So now let's look at these 3. Now, among these 3, maybe every pair of them knows each other. Maybe no pair of them knows each other. Maybe every pair of them is a pair of strangers. Well, then 1, 2, 3 is 3 people who don't know each other. Maybe some 2 of them do know each other, like maybe he knows him. Well, then 1, 2, 3 is 3 people who do know each other, right? So we did the case when there's 3 that he knows. Now let's do the case when there's 3 that he doesn't know. So then again, I look at the 3 that he doesn't know. So maybe every pair of these 3 knows each other. So then this 1, 2, 3 are 3 people who know each other. Maybe let's say this and that are strangers. Well, then 1, 2, 3 is a triple where every pair are strangers. All right, so we proved this statement. Great success. Now you can tell that there's a lot of repetition in this proof. Probably this is not the right way to do this proof. Right? There's some symmetry that we didn't observe. So let's write it down, observing the symmetry. So we're going to make a graph where the vertices are the people at the party. And I'm going to put an edge between every 2 vertices, but I'm going to color the edges in 2 colors. I'll color an edge red if the 2 vertices that this edge joins know each other, and I'm going to color this edge blue if the 2 vertices don't know each other. Okay, so every pair gets a color, and now what do we want? Well, 3 people who know each other is a red triangle. The triangle all of his edges are red. 3 people that don't know each other, the blue triangle is a triangle all of his edges are blue. So now let's say let's finally find the symmetry, but I want to prove that there is a monochromatic triangle. So if I have a graph with 6 vertices and I color the edges complete graph with 6 vertices, that means every 2 vertices are chosen, and I color the edges red and blue, then the theorem is that there is a monochromatic triangle. Okay, so now let's prove it using the symmetry. I look at my graph. Here's 1 vertex, here are the remaining 5. So then the edges from this vertex to this 5, either 3 of them are colored color 1 or 3 of them are colored color 2. And there's symmetry between color 1 and color 2. So let's assume it's color 1. And then, right, so color 1 could be red or blue. And then we say if some pair of these 3, the edge between them is colored color 1, that's a monochromatic triangle in color 1. Let's say if this is adjacent to that by an edge of color 1, then 1, 2, 3 is a triangle in color 1. if every edge between those, among those is color 2, then this is a triangle of color 2, right? So prove the same thing, but instead of saying an argument twice, we said it once, which is what you get for abstracting something. Incidentally, if you have 5 people that came to a party, then it's not true that there isn't monochromatic because of this. 5 vertices, graph of 5 vertices, some edges are blue and some edges are red, and there's no red triangle and no blue triangle. So now we prove that the rounded number of 3, 3. So what the rounded number of 3, 3? It's how big the party we need to either have 3 people that know each other or 3 people that don't know. And so we proved 6 is enough, and we proved this was prove that out of 3, 3 is most 6, and this will prove that out of 3, 3 is listed because 5 is not. Okay. So rounded here at least in combinatorics is something for general side of the party. For every happiness, there's an N, so that N people came to a party, then either R know each other or S do not know each other, or another way to say it, if I give you a complete graph of N vertices and 2 colored edges, then either there's a complete subgraph of size R whose edges are monochromatic, or a complete subgraph of size F whose edges are monochromatic. R in one color, F in another. And rounded theory tells you that for every S and T, R of S and T is fine. Now, interestingly, so R3 we were able to compute that. In general, it's really hard. Well, it's really not hard proof that it's finite. It's really hard to find it exact. So R3 we found it easy. R4 is 18. That's it. R5 there's a range. There's a range of 5. It's between 43 and 48. They don't know exactly where. And the range used to be much bigger until recently. It was narrowed down to 5 only 2017. And the people are working hard on computing something. R6, there's a bigger range. Polar, which used to make a joke about quantum numbers, is that if aliens invade Earth and they were going to kill you all off unless you compute R55, well, then you should collect all the mathematicians and all the scientists and all the engineers and send them to compute R55. But if aliens invade the Earth and they were going to kill off everybody unless you compute R66, then you should collect all the mathematicians and all the scientists and all the engineers and send them to 5 aliens. So, and then it wasn't wrong. Many years later, we're very, very far from knowing R66. But so I promised every question I mentioned, I'll try to make connections to modern math. So this is one connection. People are publishing papers trying to estimate rounded numbers. This sort of the direction is trying to compute rounded numbers for small f and t exactly, but there's also the question of asymptotically what happened. And there was a recent breakthrough maybe 2 years ago, narrowing, even asymptotically, we don't exactly know what happens. The very important example last year, shaving off a lobe or square root of a lobe somewhere. There's another aspect of this which I like very much. So in graph theory in general, there's somehow 2 directions. There's a direction where you try to compute parameters, try to estimate parameters, try to say, this graph parameter behaves in this, that graph parameter behaves in this. And then there's another area where we don't compute so. We try to understand the structure. And there's a lot of interplay between these areas because studying the structure can help us parameters, knowing how parameters behave can push me in the right direction and to describe the structure. But generally, very few people work on both, and I don't work on both. Mostly work on structure. But so this is an aspect of rounded theory. So this was all about computing. This is just another door into the same question, so structure. So we said, if you look at the complete graph, if it's big enough, then it contains a monochromatic complete structure. Now, what if I wanted a monochromatic something else, not a monochromatic complete structure, but fix your favorite graph and ask how big a complete graph do you need to have in order to contain a monochromatic copy of your favorite subgraph. So then, well, okay, so different people have different favorite subgraphs, and then you can ask, how big a host graph do you need for your favorite? How big a host graph do you need for my favorite? And two graphs are ground equivalent if the host of the same type guarantees that they're monochromatically present. And then something people think about, which pairs of graphs are ground equivalent. And again, just a few years ago, it was proved that a clique and so a complete graph, and a complete graph plus one edge are not ground equivalent. So there's a lot is going on with it. Started kind of very basic way many years ago, still a very active field with a lot of problems still unsolved. And by the way, none of these theorems are mine. I'm sort of being lax about not telling who the authors are, but the authors are not me. Okay, so let me just tell you about one more generalization. So far we talked about taking a complete graph and trying to get a two-color integration, trying to get a monochromatic structure. It turns out it doesn't make any difference if you're 2 color pages or 100 color pages. So it's still fine. You have a very big party in this thing of 100 different relations between people. These know each other, these don't know each other, these went to school together, these are married to each other, cousins with each other. It's still true that if the party is big enough, then there's a big subset of people who are in your favorite relation to each other. Okay. So moving on. Done with transit here, and now we're moving on to something else. Now the next topic is probably the most famous problem in graph theory, known as the 4-color theorem. Talk about it anyway. So this is a question that was asked by Guthrie in 1852, and so Guthrie was not a mathematician; he was a cartographer, drew maps. And he noticed that every map he later handled could be colored with at most 4 colors. Now, what does it mean? Colors? So you have a map and you have partitioned into countries, that's political map. And you want to color your map in such a way that if you look at it from a distance, you can still tell where the different countries are. So what does it mean? That if 2 countries are next to each other, you should color them with different colors. Right? And by next to each other, I'm going to mean they share an interval of a border. If they're just like this, that doesn't count. They have to overlap on the borders have to overlap on an interval, not just on a border. Okay. So Guthrie conjectured, to say today, Guthrie conjectured that for every map on Earth, 4 colors suffice. It can color the countries with 4 colors so that the 2 countries touch, they get different colors. Now I should say something, it's not exactly true. It's true. I don't know exactly what he conjectured, but actually it happened proved it in 1976. And in order for the statement to be true, you need to be a little more careful with it. The countries have to be contiguous, have to be continuous, they have to be continuous. So no Alaska, no Hawaii country consists of many islands. The examples you can make for 4 colors is not every country is just one continuous piece of earth. Then it is true that you need 4 colors. So let's just do some examples. So first of all, let's look. You have to have the 4 is necessary. You cannot do it just 2. So the top example, let's have 4 countries, 1, 2, 3, 4, and you see I've colored them with 4 colors, but you can also convince yourselves that I could not have done it with fewer colors because every 2 share a piece of the border, right? Like the outside country shares the border with everybody, these 2 share this bit, and so on. Okay, so that's an example that definitely shows that 3 is not enough, you need 4. This is a slightly more sophisticated example, because here, this country and this country, according to our definition, they don't share a border, they only share a point. But But in fact, I claim you still need 4 colors for this map. Let's see why. So suppose I could color this map with 3 colors. You see it's the same picture. Suppose I could color this map with 3 colors. Well, so I can assume the outside country is colored with color number 3. So then this triangular countries inside, I have to use colors 1 and 2 for them because they all touch country color 3. So well, let me try. I go 1. Now he has to be 2 because he now I can see touches 1 and 3. Then he has to be 1 because I can see that he touches 2 and 3. Then he has to be 2 because he touches 1 and 3. But then I don't have a color for the last one, right? So because I had an odd number of triangles in the internal region, I could not have colored this. I could not color this in this configuration with 2 colors. Okay, so at least right, at least it's this conjecture is tight. It wasn't known if it was true for a long time, but it was. It's not hard to see that you can do better. You can conjecture 3 colors. Okay, so let me wait with that for a second. Now, as I mentioned, it was conjectured it was proved by Adler in 76, and that's an amazing thing, right? Because that was, it was nice that they solved this problem, but what was really amazing is that that was the first computer-assisted proof. The proof used the computer, they were able to reduce it to a finite number of cases, and then use the computer to check each of the finite number of cases. And when you think about it, von Neumann started trying to build a computer in the 1950s. 20 years ago, Adler used the computer to prove it here. That's just unbelievable. Now, when they did it, there was somehow many concerns about whether you can believe a computer-assisted proof. Right? There's so many places to make mistakes. First of all, you can make a mistake in the code. Secondly, maybe something went wrong with the computer. The code was found, but the computer did something bad. So people were asking, is this the proof? I can't look at this proof and verify it with my brain. It's proof. So then, about 15 years later, another group tried to clean up that proof, at least to take care of the concern of is there a bug in the code. I'm not going to explain how, but they were able to do something that should calm those worries. Another thing what they did is the computer told them the right route through the proof. And once that route was found, you could verify it. You didn't verify it ahead. So that was that. And now there's a whole field called formal proof checking, where you write a software that will check your proof. You have special language and you describe your proof, and then you feed this proof into the special software, and really you can tell if the proof is right or wrong. This was special. Proof of hacking. Maybe it was proof, and maybe it wasn't the proof in the computer. Just that now it's much more well-developed and fundamental survey of mathematics. And then another survey of mathematics that we studied. Well, what if my map is not, it's not a map on Earth? What if it's a map on a more interesting planet, which is a donut-shaped planet or the pretzel-shaped planet, generally arbitrary genus? How many colors do you need there? And so it's not 4. That's just not 4. There's 7 on the torso, and that's not how many pretzel. But this started a whole new area called topological graph theory, where what you do is you don't study general graphs, you study graphs that you can draw on a fixed surface. And this is a very general graphs, they're a general function. So much you can say about it. But as soon as you tell me something interesting about a graph, like for example, draw it on the surface, suddenly all kinds of interesting things are happening, and so it's a little bit on the border of topology, you understand how topology is topological graph theory. It's a lovely and very active area. So first of all, first theory of what you got there is for every surface there's a C, so that you can color every map on that surface. We color it, and that is not a hard theory. That is not even a hard theory for the Earth, for the ball, or the sphere. But what becomes hard is what's the best thing, right? Like it's probably many of you know that it's not hard to solve that every map on Earth can be counted with 6 lines. But they're going from 6 to 4, that's really hard. So 100 years in the national computers. On other surfaces, the issue that the other surfaces, the bond that's easy to prove actually also that's possible. But those on other surfaces have branched into generally understanding graphs and surfaces. On Earth, it branched to trying to understand computer-aided proofs. Probably have two great impacts on the world. Okay, and now let me get to the last topic I want to cover. So moving on even further, now 1990s, real life. And the question is, you have cell phone towers and they transmit the different frequencies. And you want to assign frequencies to the different towers. So that if two towers have transit interfering, we will guarantee that they transmit in different. And the goal is to use as few frequencies as possible because we have to pay the government for the frequencies. So we want, as a cell phone provider, we want to buy as few frequencies as you need. Okay, so you already know that everything is going to be about graphs, and tell you right away how to turn this into a graph theory problem. You say you make a graph where the vertices are the cell phone towers, and two vertices are joined by an edge if their transmissions might interfere. Now you can ask, where it comes from, maybe some geographic location, maybe times when they're going to perform their transmission, but all of that doesn't matter. For a graph theory problem, somebody doesn't interfere, you put an edge. That's all. So here's an example. Right. In this graph, I have the vertices which are cell phone towers, and then put an edge between two if they may interfere. And then, so now what do I need to do? To every vertex, I need to assign a frequency. And I want to do it with as few frequencies as possible. Well, we call this problem graph coloring. Why do we call it graph coloring? Because instead of talking about frequencies or some other application, I'm just going to think of coloring these vertices, where my colors are going to be the frequencies. So then let's say this question in the abstract language. So given a graph, you want to color the vertices with the rule that if two vertices are adjacent, then they get different colors. Two towers. And you want to do it with as few colors as possible. Right? Because one thing you can always do, color each vertex with different color. Well, that's not a very interesting graph theory problem right now. So you want to use as few colors as possible. Then it's so now for every graph, which is how many colors do you need to solve this problem? This parameter is called the chromatic number of the graph. It could be known by chi. Something that's not difficult to notice, and that's called the kind of introduction, that if you have a graph, then its chromatic number is at least what's called the number, which is the number of pair vertices in this graph. Look at the graph and have the number of pair adjacent vertices. If you look at the graph and you notice that there are 100 vertices, every two which are adjacent, then each of these 100 vertices needs to get different color. Adjacent. So your chromatic number is going to be at least 100. Okay, so this is an easy fact. Now, in math, when you have an easy inequality, what do? Start asking about cases of equality. Okay. So easy to prove that this is always at least there, then there must be something interesting in the concept. Is the omega colors always enough? Always true that you can color a graph with as many colors as the number of pairwise adjacent vertices in it, and that there is no flow. Let me give you an example. Let's look at this graph. So this is a cycle of length 5, right? You put 5 vertices on a cycle, on a circle, and you make consecutive ones adjacent and non-consecutive ones non-adjacent. So then let's ask 2 questions. What's the biggest number of pairwise adjacent vertices? Well, that's not hard. That's 2, right? Only consecutive pairs are adjacent. How many colors do you need to color this graph? Well, I claim 3, because if I try to color it with 2 colors, you go 1, 2, 1, 2, and you're stuck. You remember, it's similar to what we had in the map coupling. There's a reason for that. Okay, so C5, the cycle of length 5, does not have the property that you can color it with omega colors, because omega is 2 and chi is 3. Okay, let's do one more. Let's do C7. Let's put 7 vertices on the circle and make consecutive pairs adjacent and non-consecutive pairs non-adjacent. So the clique number is again 2. It's just consecutive pairs. Well, the chromatic number, well, same deal. You go 1, 2, 1, 2, 1, 2, and you're stuck. So you need 3, and you could color with 3. Now let's generalize. Let's make C2k plus 1. Let's put an odd number of vertices in the cycle, 2k plus 1 vertices in the cycle, and let's ask about the clique number and the chromatic number. So, sorry, make consecutive ones adjacent, non-consecutive ones non-adjacent, and let's ask about the clique number and the chromatic number of that graph. Well, same deal. Consecutive pairs are the only adjacent pairs, so the clique number is 2, and the chromatic number is again 3, because for any odd number, if you go 1, 2, 1, 2, 1, 2, 1, 2, you're going to get stuck. Okay, so here's an example where, where the clique number and the chromatic number are not the same. The chromatic number is strictly bigger than the clique number, and the strong perfect graph theorem tells you that this is the only problem case. Now you need to be a little generous with what you mean by only, but I'm not going to explain that. But basically, this is where all the problems lie. If your graph does not have any of those, you look at a big graph, you cannot find a configuration that's an odd cycle, and then there's another one that's closely related to odd cycles, then it is true that in your graph, this thing also the plot, chi and omega are the same. And this is known as the strong perfect graph theorem. Thank you. And some questions, some comments.
Well, since you're giving us the story about all these things, where do like Voronoi triangles come?
I don't know. Sorry. You caught me. The best spot. It's a triangulation of the plane somewhere in that area.
So, first, let me thank you for being one of the speakers who didn't start the very exciting mark when I was young, but it seems to be a recurring topic here. But so we do know that the solution of the Challenger problem and then Baker theorems left the beginning of the drive to forward. So many of these things you're describing have connections with mass weights. Did they give any development of different subjects? Any of these problems of graph theory to expect?
So you're asking, is there a graph theory that helped develop algebraic topology?
Well,
Or some other area?
So did we see out of these problems some additional invariance, maybe not in the cores, but in other parts.
So there is something called graph polynomials, so generating functions, which you can say came from here and they're used everywhere. When you think about visual complexes, at the end of the day, what you look at is the graph of the visual complex, then maybe do the same thing in higher dimensions. Line of thinking, thinking about higher dimensional object and then its boundary, which is a lower dimensional object. This is kind of the start of that. Regions in the plane. We have, its boundary, which is the set of edges of the boundary. We have Euler characteristics. Presumably came from here, I'm not sure. But now it's much more general thing. Some the first three things I can think of standing here, maybe.
There by now, non-computer group of the four color here.
No, there isn't. Everybody would like to. There's a formally checkable computer. And yeah, I don't know. I mean, I think somehow with time people will be less and less motivated to do it. Like even when I was there, so 20 years ago, it seemed like such an amazing. It would be such an amazing accomplishment to try and get a handful of the four color there. But now that there's a formally checkable computer proof, I'm not sure it's so important.
It still would be nice to have a more conceptual understanding.
Yeah, that's true.
Just not just a curiosity based.
Yeah. Yeah, look, I wouldn't object. When they did it, especially fibers, don't object to it.
Thank you very much.